A gas has a volume of 3.75 liter at 20 degrees Celsius and 0.888 atmosphere. What volume in liters would it have at 135 degrees Celsius and 1.20 atmosphere? Okay, so this is a gas problem, and we're looking at the same gas sample under different kind of condition, and apparently volume would be changing as we're looking for a new volume. Temperature already changed, and pressure changed as well. So we have a bunch of numerical conditions. Before we go any further, let's look at exactly what we have. Let's make an inventory count. So first set of condition, we're going to label it as 1. So we know V1 is 3.75 liters. And then, of course, we also know that T1 is 20 degrees Celsius. Now, and knowing that in all gas calculation, temperature-wise, we're going to be using Kelvin, so we might as well turn it into Kelvin right now. 273 plus 20 is 293 Kelvin. And then, of course, P1 is 0.00888 atmosphere. Now, all three conditions are in the standard condition that we use in our ideal gas law: liter, Kelvin, and atmosphere. Now, all right, this is the first set of condition for the gas. The second set of condition, we're going to label them as 2. So there's V2, which is, what do we want? How many liters? And then T2 is 135 degrees Celsius. Again, we're going to turn it into Kelvin, which gave us full 8 Kelvin. 135 plus 273. And then P2 is 1.20 atmosphere. So these are the conditions that we have, 5 conditions that we have, and the 1 condition that we are trying to calculate. Now, how do we set it up? Now, well, remember, we're talking about the same gas sample, which means for each set of a condition, the ideal gas law got to stand. PV equal to nRT applies to both conditions. Now, of course, so that means P1 V1 equal to N1 RT1, and P2 V2 equal to N2 RT2. Well, how does that help us? Now, think about it. This is the same gas, which means N1 definitely equal to N2. There's no change. And okay, if I divide the two equations, left side to left side, right side to right side, that means this equation still stands, and N1 and N2 is now on top and bottom, which means since they're the same, we can cancel. R is a constant. It's always the same. So R is gone. So now this equation turns into P1 V1 P2 V2 equal to T1 T2. Let's see. That's the 6 things that we listed here. Out of the 6, we know 5, and we want V2. Well, that's a simple rearrangement. Rearrange the equation, we get V2 equals to P1 V1 T2 over P2 T1. Make sure when you rearrange the equation, you label things right, because one mistake here would cause the whole problem. Alright, so once we got the setup, now it's plug and chug. Throw things in there. P1 is 0.888 atmosphere. V1 is 3.75 liter. T2 is 408 K. P2 is 1.20 atmosphere, and T1 is 293 Kelvin. Okay, atmosphere cancel, Kelvin cancel, and we know we're going to get a unit in liters, which matches our volume calculation. Punch numbers into calculator, keep your 3 sig figs. In the end, we get 3.86 atmosphere. So under the new, 3.86 liter. So under the new set of condition, the same gas sample will be occupying 3.86 liters of volume. And this way of getting individual gas laws from the ideal gas law is a very common practice in gas calculation. As long as you're dealing with the same gas sample, you can always set up two sets of conditions and divide them by each other.